Good evening. My name is Anvesh, and I'll be taking the second out class session for the course Interfacial Fluid Mechanics. Uh, so before I begin, the the last date for assignments for week 1 and week 2 is tomorrow. Uh, Therefore, I'll be taking the doubts as well as the questions of assignment 1 and 2 in the next lecture. Uh, so for today, we'll go over a important derivation for the theorem that has been used in class. This is a theorem that was used when we convert the line integral emerging from the surface tension uh, term to convert it into a surface integral. That is, the line integral is converted into the surface integral. We see that this expression is used directly in the class, and but there is some merit in deriving this equation. Therefore, I'll go over the derivation. Uh, so the to begin, the term here is the surface tension force that is experienced by the interface on the surface, and this term is converted into the surface integral as we have seen. But how do we get this? So we know that the Stokes law or the Stokes theorem is used to help convert a contour integral as shown here into a line integral. But if you notice, these are in terms of the vector f, and but we need it in terms of the surface gradient terms as we see here. So I'll set up the problem. We have a interface as seen here, and then as seen in the class, we have this relation. So the idea is that we use the Stokes law, the Stokes theorem, and start our derivation and get to a suitable form that can be used to um, get the desired result. I'll start off. So first I'll just write down the begin to begin our derivation. We start off from a fairly separate starting point, but as we go along our analysis, we'll see how we use that later to substitute surface tension. Here, surface tension is gamma. Here, here in this law, f is a vector and n is the normal vector to the surface ds. If we see above, n is normal to the surface. So let us assume that f, okay, f is a cross product of two vectors, that is f cross b, where we assume that b vector is completely arbitrary and constant. We'll see how we can use these. So we substitute f into the Stokes theorem. Then we get for us the surface integral that we are taking. I'll redraw the diagram. Uh, so if we take a small length dl, then m is the direction of the vector dl. Then we can write it's a dot here. Then it will be now from vector algebra. We have two specific expressions that we'll use, where we can say cross b cross dot m is equals to minus b dot f cross m. We see that when we change the order to 2, 1, 3, we get a negative sign, and the cross product and the dot product have been switched. So this is fairly easy to show, and can be easily shown using Einstein notation. So we'll substitute firstly this into our expression. Then we have minus b and vector Yeah. Okay. We can't replicate it. Integral must be must dx. We have substituted the result. Similarly, another uh, another expression for del for del cross f cross b is equals to f vector del dot b minus b vector del dot f plus b vector grad f minus f grad. Notice there is a dot between b vector and grad f and f vector and grad b. Uh, Grad of a vector f will give a tensor which is uh, which is dotted with a vector b, which in turn is a contraction and will give us a vector again, and therefore it's the expression is consistent, and also this can be easily verified using Einstein notation. If you also notice here, this is a vector as uh, del cross f is a vector again. Cross with another vector b gives us a vector, and here also it's a vector. So the expression is consistent everywhere. Now we'll use this and substitute it into our initial equation. I'm highlighting the expressions that are being used. These can be verified using Einstein notation easily. If in case there is any trouble, I'll take this up in the next class. So using this equation, substituting f of minus c. Okay, the minus is still inside. Uh, Sorry, I have missed a dot product here. Uh, Please uh, make sure there is a dot. So minus, also it's a vector, minus b dot f cross m hat dl is equals to integral s, where n hat is dotted with f vector divergence of B minus B vector divergence of F vector plus B dotted with grad F minus F dotted with grad. Okay, now if you notice here, we assumed that our B vector is arbitrary and constant. B, or more precisely, constant and arbitrary. Owing to the fact that B vector is a constant, the terms del dot B vector, that is divergence of B, is identically equal to 0. Similarly, gradient of B will also drop out. Therefore, making the simplification and rewriting, uh, minus B vector dot F cross M dl over the contour is equals to surface n hat dot. Now substituting the terms, sorry, substituting the terms, dropping out the terms that are 0, we have minus B vector with divergence of F plus B dotted with grad F. Yes. Now, as B vector is arbitrary and constant, we can get it out of the integral, and doing that, integral as it is constant, we can write minus B dot F cross M hat. This is a unit normal. M, remember, is the unit normal in the direction of F, and dl, which is equals to B dot surface integral on grad divergence of F plus simply grad F. Yes. As now we have said in the initial statement as an assumption that B vector is completely arbitrary, we can directly compare two integrals. So rewriting So, so we directly compare the integrals here, namely this and this. We get that f cross m dl is equals to, the minus is there, is equals to integral s. We have integral s and divergence of f plus. So this is what we will get. Let's just check. And sorry, there's a slight mistake here. The n here is the n here is on the entire term. Therefore, I've missed out the n dot here. Therefore, okay. There's an n dot here, and now we have completely eliminated b, which was arbitrary from our from the derived expression. So now we'll use the fact that we have f and is crossed with m. If we notice early on for the surface here s, the surface s, uh, for the surface s, we know a priori that n hat cross m hat is equals to negative of t. So if we use this, uh, so there is a small change here. Um the negative from here, we have missed the negative. The negative, if we take b minus b out here, we have a negative sign here. Minus n hat dot grad f. Okay, only then we can compare term 1 and term 2, as both these terms are same. Okay, so now we have a negative sign here. Uh, Now the expression is correct. So we know a priori that n cross m is equals to minus of t hat, where n is the normal to the surface, where n is normal to the surface, and m hat and t hat are the tangents to the surface. So, starting off from the Stokes theorem, we have assumed f to be small f cross b, where b is arbitrary and constant. And upon replacing it into the equation and uh, using some standard vector identities, we derive to this equation, from which b has been completely eliminated. Uh, Hello, can you hear me?
Yes, hello. Hello, am I audible?
Uh, can you repeat, please?
Yes, you are audible. I can hear
Okay,
you.
okay. So, okay, actually, I was just going over a derivation. Actually, the assignments for week 1 and week 2 are due tomorrow.
Yes,
So, I can't go over the solutions for that. So, I was just going over a particular derivation. Uh,
okay.
okay. I'll just repeat what I've just said. I'll just quickly go over it. Okay, for the benefit. If you have any query, you can ask. You can stop me and ask.
Okay, I'll
So, have you gone through the lectures of week 2?
actually, I think, yeah, I have made notes to summary of equations. Yeah, I have gone till week 2, but I need to just, uh, like week 1, I was able to go thoroughly, but the week 2 part is still left from my to
Okay,
be.
okay, that's okay. Okay, you have any questions, you can ask.
Yeah, so I'll just ask and you can continue. I'll let you know.
Okay, okay. Should I
Because I just,
just repeat this?
yes, if you can, please.
Okay, okay. I'll just quickly go over it. So, this equation that is written here, that this is there in week 2, where we introduce surface tension in the momentum equation. And you see this particular term. in the momentum balance equation, and we convert it into a surface integral. So the dl is converted into ds, and this particular expression is directly given to you in the lectures. So what I am doing here is to see how we can convert this integral, line integral, to a surface integral. So you might already know the Stokes theorem or the Stokes law, which is used to convert a contour contour integral to a surface integral. Just surface integral. So, but the form that is there in the lecture or the lecture notes is different, and that is specific to the kind of geometry that we have taken, and I was just going over it. So, firstly, to I start from the Stokes law, where we already know that the Stokes law is given by this equation, and we assume where f is a vector and dl is the arc length, and f is a vector and dl is the arc length, and then n is the normal to the surface that is taken, and we see that the dot product changes into a curl of f vector here. So for deriving this particular form, we start from here, where we see capital F, where we assume that capital F is a cross product between two vectors, small f cross b, where the speciality of b is that it is arbitrary and constant. So once we substitute f cross b we substitute this into the equation here, then we see that we get this form. And then by using two of the vector algebra identities, those are this and this, we have got to the form. We got this particular expression, where I'll remind you that m m is a tangent unit vector, and n n cap m cap and m cap and n cap is the unit normal vector. So we get this form, and then if in case you remember, or maybe if you don't remember, in the class it's already established that n cross m is equals to negative of the tangent vector. Here both Here again n is normal to the surface, and m hat, m cap and t cap are both tangents to the surface, where m is in the direction of the vector f. Okay.
Yeah.
Okay. So I'm basically trying to get this form. So now f, I will give real values to f. So here let us assume okay, f vector is equals to gamma times. So here we choose f to be gamma times n cap, where gamma, sorry, Then substituting it into the equation, uh, given the equation 2, we have, okay, here there is no negative. Sorry, there is no negative. Now we have gamma n cap cross n cap dl, which is equals to, this is the contour integral n cap, sorry, n cap divergence of gamma times n hat minus n dot gradient of gamma times n cap. Yes. So once we have this um, this can be written as negative of t cap, as we have seen earlier in the starting. And similarly, these terms need to be expanded. So we get two terms from here and two terms from here. So basically, we need to write four terms for the del operator on top of the surface tension gamma and n cap. So as okay, I'll write down the terms and then explain. So we have sorry, we have gamma times minus t cap dl, which is equals to s. Uh, we have n hat. We are looking at this term. So we have dot stars. We first have gradient of gamma n, and then plus gamma times del dot n. Okay, so here while expanding del dot gamma n hat, we have first we have this is a vector which is dotted with n hat, plus we have divergence of n, which is multiplied with a scalar gamma. So all in all, this is a scalar. So that is consistent here. Then we have the terms minus n cap dot uh, gamma n cap del gamma minus we have n dot n, and then we have negative n dot So these are the four terms we have. One, two, three, and four. So if we look at these terms, the term, the first term, uh, dot n cap. If we visualize this term, this particular term, generally the surface tension, if we look at this surface S, the surface tension generally acts on the boundary, and any surface tension changes will be present on the boundary, on the interface. There won't be any surface tension gradients or surface tension, for the matter of fact, in the bulk, in the upper fluid or the lower fluid. So if you think about it, I'll just redraw it here. So the surface tension acts only on the boundary, and if there is any surface tension changes, or surface tension is a function of the surface of the interface, then the changes, the then grad of surface tension will always point in the direction of the interface. And if we see that how the and if we see how the normal vector looks, then the normal vector will always be, the unit normal will be always perpendicular to it. So at all times for an interface, the angle between the, okay, I'll switch to green, angle between grad gamma and the normal vector n is 90 degrees. This is a crucial point here, and due to the artifact of the grad, the grad of surface tension gamma being perpendicular to the normal vector n, this term can be this term is always equal to 0. Therefore, this term drops out from the equation. Similarly, we look at another term here. So another term which we'll look at is number 3. If we look at number 3, it is basically the term 3 is, I'll just copy it from here. So this is same as gradient of gamma n hat dot n hat. Um, sorry, we are looking at the wrong term. Sorry. Let's delete. You have any doubt?
No, no, the one that you wrote was like third term in that n dot should not be there, probably. That's the one that you just deleted.
Okay, that's okay. I made a mistake in copying. Wait a second, I'll just redo it. Okay, we have to look at the term 4, not 3. To look at the term 4. Okay, so the term 4 is this one. This is the term. I'll just rewrite it as it is n hat dot gamma grad of gamma. Okay, so here gamma is a constant. So okay, grad of grad of n cap. Okay, now is it okay? I've not made any mistake. Uh,
Yes, yes.
okay, okay. So now here gamma is a constant. So I'll write gamma first, and then we have n cap dot of n cap. Okay, so let's just look at what is del of n dot n, which is equals to n. If we open up using product rule, we have n cap grad n plus n, here dot will be there, n cap dot grad n, which is equals to 2 n cap n n cap dot grad n. So we see that uh, gradient of n cap gives us twice n cap dot grad of n. So these two, okay, not the entire thing. These two are same. So substituting this back into the equation, we have, which is equals to gamma. There will be a 1 by 2 gradient of n cap dot n cap. which is equals to simply and gradient of any constant is equals to 0. So again we see that the fourth term drops out. Uh, this is identically equal to 0. So I'll just copy this. So now we have this equation. Rewriting this equation, I'll just rewrite gamma e cap BL is equals to surface integral cap gamma del dot n cap dot n cap gradient of S. Okay. So this is after the simplification. And now if we see here n cap dot n cap can be written as 1. Substituting this here, yeah, we have minus C gamma PL is equals to integral over the surface. We'll write gamma first, gamma n cap of divergence of n minus gradient of the gamma vector. Yes. So this is how we, okay, I'll take the negative sign also the other side. So the contour integral of gamma times the tangent vector is equals to the surface integral of gradient of surface tension gamma is negative of gamma times n cap to del dot n. Okay. So we have finally arrived at the initial expression that we wanted to derive. I'll make a box here. Uh, so this was the equation that we wanted to get, that gamma times the tangent vector times dl is equal to the gradient surface gradients of gamma minus gamma times n cap, the normal vector, into the curvature term, which is del dot n cap. So if you notice here, this particular term, del dot n, del dot n cap, del dot n cap is like the curvature, and we also incorporated the effects of surface tension gradients. So the line integral here, or the contour integral, has both the surface tension gradients part, that is the first term, and the curvature part, which is the second term. So if you remember the Laplace equation, which is basically delta p is equals to gamma times surface tension times 1 by r, which is the curvature, 2 times curvature, which is basically for a spherical body. We get curvature, yes, and this is for when surface tension is constant, but the above term that was derived is for both surface tension gradients and the curvature of the interface. Okay, do you have any doubts?
I have a doubt related to the topic where surface tension was introduced in the
Okay,
lecture, in which
okay.
said like Professor told about just 1 minute, I'm just referring to my notes.
Talked about, I can't
Just
hear you.
yeah, just 1 minute, please.
Okay, okay.
Yeah, where Professor told that repulsive forces are less sensitive to local molecular arrangement, and like we really talked about repulsive and attractive forces. So he was trying to explain the surface tension phenomenon, which we generally know. So why is it in that part? I got something like repulsive forces are very short range and attractive forces are slightly large range. That topic really talked about that.
Okay. Uh, okay, I'll just scroll it.
Just about that. There you go. Just about.
Okay, here. Okay. Um,
At the interface, I just want to ask where is the repulsive force coming in? Like he has shown with black arrows also on the at the
Yes.
interface where he has shown the sphere. So
Here.
uh, what are those repulsive forces? How they are coming like inside the liquid? It should be the attractive forces only. I think, as far as I think, I'm not sure on that. I was confused on that part.
Okay, okay. Okay, this is okay. I'll I'll see. I can write here. Write. 1 second.
Sure.
Okay, not tangential. Okay. I'll just try to see if I can make sense. Okay. So near the interface. So one is that it's in the bulk. Yeah, let's make it in the bulk, and red is repulsion, and black is attraction. So basically, repulsion from other molecules and repulsion, strange, attraction. I can write it in the same color. Long range. So black, he says that this is the attraction force. Yeah. So this is for the bulk. Is this okay? You agree with this? We'll try and figure it out. I'm also not sure.
Actually, I'm just curious, like, why is the repulsion coming in? Like, if the molecule is, like, maybe that's a cohesive force that I has, so it should be only attraction. Why repulsion?
Okay, so you are okay with the force balance, is it?
Just, I mean, not sure why both type of forces are coming into picture, like repulsive also and cohesive
Okay.
also.
Okay. So is okay, if I try and understand, is okay, 1 second. does this graph make sense to you?
No, not really.
No?
Not really yet.
Okay, okay. So, okay. I'll- So, okay, first we'll, yeah. Okay, so if you think of uh two two particles, okay, they are separated by a distance r. I think that's what is given. And then if you start reducing r to 0. Okay, first we'll look at the case where r is finite. When r is finite, okay, I'll make the graph also. One second. The graph. So at a finite distance, we see that there are van der Waals. You are aware of this particular phenomena?
Yes, yes.
Yeah, so when you are at a finite distance, but close to, I can't exactly pinpoint an distance, but when you're close to it, you have van der Waals force of attraction, which is maximum here at RA. So here we see van der Waals forces of attraction, and then this is called as the long range force. And as we go closer and closer, you feel the effects. Don't have space. Okay, so first let's make attraction. So we have two, let's say we are looking at the molecular level. So this is the proton and this is the electron cloud. And then similarly, the molecule here, same size. When they are at a certain distance r, this proton here feels the electron cloud. Okay. So this proton here P feels the electron cloud here, and this causes attraction. And when this is at a certain distance r, and when you get close enough, you have a proton here. Oh. And you have the electron cloud. Here in this case, you see that both the electron clouds are clashing with each other, as well as the proton here also feels the repulsive forces. So basically, this is the origin of the attraction, long range attractive forces and the close range repulsive forces.
This makes sense.
I can't hear you. Can you repeat?
Yeah, I think this makes sense. I think I'm able to go. I mean, I find it understandable.
I can't hear you. Can you repeat, please?
I mean, it's fine. I mean, I was able to understand what you were trying to convey.
Okay, this is how you get that graph. This is done at a molecular level, and this is how the graph is generated.
Okay, okay. Thank
The
you.
repulsive and the attractive forces. We are talking about the order of magnitude of uh micro, maybe basically the atomic length. When we are order of magnitude of that, when we are really close to that, then we have repulsive forces, and when we are a little further away, we see the van der Waals forces. These are the same forces that you might have studied about this in. Uh,
Yeah, I could not recall at that moment, but when you
okay,
made
these
this
are
like,
the same forces. This is the origin of the surface tension. That's what he wanted to say there.
okay,
And then if you have understood the force balance, then there is no problem. That is mainly the force balance is you have to understand the force balance.
yeah,
Okay.
yeah.
Okay. Is there any other question you want to ask? You can ask.
Not as of now.
Okay. 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 If there is anything else you can ask, or else I can't take the questions of week one and week two today. So I'll take them up in the next class.
Okay, next class will be on next Tuesday.
Next Tuesday, yes. There I'll take the questions of week one and week two. I hope you don't have any problem in the week zero. You can ask them.
I submitted week 0, week 1, week 2 still left behind.
Okay. Okay, I won't be taking anything else. If you want, uh
Okay,
you
okay.
can leave the meeting.
Thank
I've
you.
okay.